All chemical reactions require energy, and that is a key component to really a lot of chemistry, is trying to figure out how the energy that is needed for a reaction to take place, what is happening with the energy. And so the way we're going to look at this and how energy plays a role in chemical reactions is looking what exactly a chemical reaction is. Chemical reactions are all about bonds breaking and forming. And for that to happen, energy has to either be put into a reaction or energy gets released. Now, the way we calculate and measure this energy is through a term that we call enthalpy. Enthalpy is basically the net change in a chemical reaction. And we symbolize enthalpy with the letter H. And so since it's a change in energy, we will use a symbol for change, which is the Greek symbol delta. So delta H being the change in energy. And so this is what we call the enthalpy of a reaction. Now, like I said, enthalpy, or the change in energy, is all about bonds breaking and forming. So when a bond breaks, what exactly has to happen? Well, let's think about that. If you have a bond, those atoms want to stay together. So for those atoms to separate into individual atoms away from a compound, we have to put energy into it. And so to break a bond requires energy. So breaking bonds require energy. Once those bonds have broken, then we have all these individual atoms. Those atoms will then come together to form new bonds. When atoms come together to form new bonds, then energy is going to be released. And so bond formation is energy being released. Breaking bonds require energy. When bonds are formed, energy gets released. So when bonds break, that means we have to put energy into it. And when bonds form, energy comes out. Okay, let's look at a generic reaction where we have some make-believe compound, A2, and another make-believe compound, B2. They're going to react together to make this AB compound. Well, for this to happen, A2, the A's have to break apart. B2, the B's will have to break apart. Then they will rearrange to make AB. Now this should be a balanced reaction, so we do need to have a 2 right there to show that we have 2 of those to kind of satisfy the law of conservation of mass. But if we look at, let's just look at the energies. If we look at just the energy of the reactants, let's say the reactants have some energy. And if we make a graph where the y-axis is energy and the x-axis is kind of the progression of the reaction. So as the reaction happens, well, the reactants are going to have some type of energy. So we don't know what, and it's some random energy. I mean, it just has some energy value. Now, if we put energy into it and eventually those products, the reactants will break apart and the products end up forming, and those products, let's say we have AB, end up with a higher energy than the reactants. So this here is our reactants and this is our product. If the reactants have some energy and then once the products get formed and the products have more energy than the reactants, then that means ultimately we ended up putting energy into this reaction. And so we had an increase in energy here overall. When you have an increase in energy, that means energy was added. So energy got added, energy got put into it. And so we have a special term for that type of reaction. This is what we would call an endothermic reaction. An endothermic reaction is basically where the reactants have some energy, the products have some energy, and the products end up having more energy than the reactants. So that means energy got put into the system. And so that is what we call an endothermic reaction. So let's pretend let's put some values here. let's say, for example, the product had an energy of, I don't know, let's say 12 kilojoules per mole, and that the reactants had an energy of, let's say, 8 kilojoules per mole. And these are just arbitrary values here. And so what would be the energy of this reaction? What is the delta H for this reaction? Well, delta H, which is our enthalpy, is going to be the reactants, which is 8, and our products, which is 12. So we ended up with 12, and if we subtract that 8, we end up with a total of 4 kilojoules per mole of energy. That means that the products increased by 4 kilojoules per mole of energy. And so this ends up being a positive value. And so whenever delta H is positive, it is considered an endothermic reaction. Now, another way we could write this or think about this is we have our reactants, and we basically added energy. Our reactants plus 4 kilojoules per mole produced products. And so this is kind of another way of writing this chemical reaction. We have our reactants, and we added 4 kilojoules per mole of total energy, and then we ended up with products. And so here, our energy is kind of the part of the reactants part of the chemical reaction. And so that is also indicative of it being an endothermic reaction. Now let's do the opposite. What about if the energy is released? So let's say we have our graph, and our y-axis is our energy, and our x-axis is the progression that happens with the reaction, and our reactants is some energy value. And then this time, our products end up being less than what the reactants were. And so what happens here is we put energy into the reaction, the reactants bonds were broken, and then when they formed back up, the energy of the products, total energy, ended up being less than the energy of the reactant. And so what happened here is energy, law of conservation of energy says that energy can't be created or destroyed. So we put energy into it and energy got left. And so here, this tells us that energy kind of left the system. And so if we look at this, energy left by that amount. It left this difference between the reactants and the products. And so here, we ended up with a decrease in energy. And so with a decrease in energy, that means energy left. And so we call this an exothermic reaction. So you can also think of it as exo, exiting the system. And so energy left or exited, and so it is an exothermic reaction. So here, our delta H value will end up being negative. And so let's kind of show that how it's negative. Again, let's make some arbitrary values here. So let's say our reactants are, let's say it's 10 kilojoules per mole, and then our products end up being 4 kilojoules per mole is the energy of our products. And so our difference then, our delta H, will end up being 4 kilojoules is what we ended up with, minus what we started off with, which was 10. And so this is a minus 6 kilojoules per mole. And so notice that we used the negative sign here because we got a negative. We ended up with 4, we started off with 10, and so that ends up being a negative 6. And so negative corresponds to an exothermic reaction. So how can we actually get these values, these numerical values? Well, to get those numerical values, we have to look at individual bonds and how those bonds, how much energy is needed to basically break those bonds. And there are lots and lots of tables that give values for the bond formation of different atoms coming together. Now keep in mind, every table is going to be slightly different because bond energies are in essence kind of averages of all the bonds. And so if the bond between two atoms, might be a little bit different in different molecules because there's other factors in play besides just those two atoms. So for example, you might have the OH bond. Well, an OH bond energy is going to be not exactly the same as in water as in, let's say, in alcohol. There's OH bonds in alcohol, there's an OH bond in water. Those two compounds are going to have slightly, they're not going to be drastically different, but those bond energies will be slightly different. And so we have these tables that kind of throw in all the averages of all these different molecules that contain these types of bonds. And so not every table is going to be exactly the same. So the examples that I do here may not match exactly the tables or numbers that you might find in your own book. So let's look at an example here. Before we really look at bonds forming and breaking, I want to kind of go over this idea of the positive and negative exothermic and endothermic reactions and how we can determine that from a equation. And so let's do a reaction here. Let's say we have a reaction of 2 moles of hydrogen gas reacting with oxygen gas. And this reaction is going to form 2 moles of water vapor. We're going to do liquid water here. And this actually is going to have 565 kilojoules per mole kind of as our product. So if 565 kilojoules per mole is part of the product, is this an exothermic or an endothermic reaction? Well, since this energy is a product or a part of the product process, then that means that energy kind of was released. Energy left. It is a product. And so since this is a product, energy kind of was left or left the system, then this ends up being an exothermic reaction. And what would be the sign of delta H? Well, delta H would be negative, and it would be negative 565 kilojoules per mole. And so what about the other scenario? Let's say we have nitrogen, and we have a nitrogen gas reacting with some oxygen gas, and this will have 188 kilojoules per mole in our reactants to form 2 moles of nitrogen monoxide. So here, energy is part of the reactants. That means we put energy into it. Energy was part of the reactants. We had to have energy for this reaction to happen. And so since we had to have 188 kilojoules per mole for this reaction to happen, that means we put in that much energy, and so this is an endothermic reaction, which means that the delta H value is going to be positive 188 kilojoules per mole. And so this is how we can look at delta H or enthalpy, the change in enthalpy for reactions, and how we can incorporate it in the chemical reaction itself. Now keep in mind that we kind of put these numbers here as reactants and products, but they're not true reactants and products. It's just kind of to help us categorize or tally the energy needs of this reaction. We can't just simply take out this amount of energy like we do or think about the actual elements and compounds and molecules. This is just kind of a way of helping us decide, all right, is this energy that's needed or is this energy that's being released? And that is the whole purpose of putting the energy as a product or a reactant. All right, so now let's do a problem where we actually are looking at a reaction and trying to determine the actual delta H value, how much energy is required or being released in this reaction. So we're going to look at the reaction of hydrogen gas reacting with iodine to make 2 moles of hydrogen iodide. Now, if we look at this reaction, we have a hydrogen molecule. That hydrogen molecule, we have a HH, so a hydrogen atom and a hydrogen atom are bonded together. And so we have to break that bond. And so what we have is one hydrogen bond that has to be broken. And if we look on tables, we find that the HH bond is about 436 kilojoules per mole. So that's how much energy is needed to break or to separate out those hydrogen atoms. Well, to react with the iodine molecule, that iodine molecule also has to break apart into separate iodine atoms. And so we have one iodine molecule, and so therefore we have one iodine bond. And if we look on a table, we find that the II single bond is about 151 kilojoules per mole. And so if we look at this, then for these atoms to separate out from their individual molecules and to break those bonds, we have to have a total of 436 plus 151, and when we add those two together, we get 587 kilojoules per mole. So that tells us that we need 587 kilojoules per mole to break that hydrogen bond and the iodine bond in a hydrogen molecule and an iodine molecule. We have to have this much energy to break those bonds. So that's how much energy is needed for this reaction to happen. But the product is an HI molecule forming. And so when bonds form, that means energy is being released. And so what bond is being formed? Well, we're forming an HI bond. And then we're actually forming two HI bonds. That's why we have a 2 there. And so we have two HI bonds, and when we look on a table to see what the bond energy of HI is, we see that it's about 297 kilojoules per mole. Again, these values may differ from whatever table that you're seeing, but they shouldn't be that far off. They should be fairly close. So we have 297 kilojoules per mole for HI, and now we have 2 of those. So we need to multiply that by 2. So 2 times 297 gives us 594 kilojoules per mole. And so that tells us that when that HI molecule was formed, 594 kilojoules per mole was given off. That's how much energy was released whenever those two hydrogen iodide molecules were formed. So then what is the total enthalpy? What is the delta H for this reaction? So let's kind of figure this out graphically and kind of let's look to see what's happening. So again, we're kind of going to have our energy here as our y-axis, and then we're going to have our y-axis for the progression or how the reaction proceeds. So I'm just going to put the word progression, and it's just like the beginning and end. So the beginning is going to be on the left-hand side, the reactants are on the left-hand side, and the products are on the right-hand side. So our reactants start off with some energy. We don't know what that energy is. This is a totally arbitrary scale. But what we do know is it required 587 kilojoules per mole to break those bonds. And so we have to increase this by 587, and so this right here ends up being 587 kilojoules per mole. So we had to put 587 kilojoules per mole of energy into this reaction. And then when the reaction happened, then 594 kilojoules per mole was released. Now that's going to be a little bit more than this. So that means our products are going to be a little bit further down. And so this is our products that have formed. This was our reactants that we started off with. And so if we look at this right here, and this difference, that difference is 594 kilojoules per mole. And so it required 587 kilojoules per mole for the bonds to break, and then when the bonds formed, it released 594 kilojoules per mole. So what is delta H of this reaction? Well, delta H is basically the difference between the products and the reactants. Our delta H is going to be, it took 587 kilojoules per mole of energy, and we left or released 594. And so remember, when you release something, it's going to be a negative value. So we're going to subtract 594 kilojoules per mole here. So we will always subtract what bonds were formed because energy is always being released whenever bonds form. And so 587 minus 594 gives us minus 7 kilojoules per mole. And so since it's a negative, and it should be negative because the products ended up being below the reactants, it decreased by 7. So we can kind of look and kind of draw this line out like this. This difference here would be 7 kilojoules per mole. And so that's the difference between the reactants and the products. And it decreased by 7 kilojoules per mole, which tells us that this was an exothermic reaction. And so that is the delta H for this reaction.